table that maps the service to the mechanism based. Okay, Bismillah ar-Rahman ar-Rahim. So, so last time we talked about chapter 1. We talked about some basic definitions related to what computer security mean, what communication security mean, what security service and security mechanisms are, and what is the relationship between the security service and how we can realize the security service using one or more of the security mechanism. And we talked about certain criteria. So today we'll continue the discussion in chapter 1. We talk about attack surface. So attack surface is actually is any reachable, so any reachable and exploitable vulnerability in the system, whether in the network or in the software or in the hardware, and so on. So if we have open ports, that's a vulnerability, or it's an attack surface which can be exploited by the attacker to try to get into the system and hack the system, whether this port is for web and other servers. Like for example, we all know that HTTP port 80 has to be always open. That's very common, and there is no way around it. So we have to have this port for HTTP service. So this is number 2. Any service that's available inside of the firewall. So the service of HTTP is open on port 80, which creates some kind of attack surface. Code that processes incoming data, for example, any JavaScript. So you know that while you're browsing the internet, you can view the source of any web page and get to the JavaScript. It's actually exposed, so it's open. You can read the code or the software there, in which case you can consider this an attack surface. So if I know the code and what the logic that the code uses to process the data, I can use that to attack the system. Or any human error. So we can classify the attack surfaces into one, network attack surface. So the first two, they describe the first category here. Network attack surface is that refers to a vulnerability over the enterprise network. So anything that involves communicating a service or a port over the network is can be considered a network attack surface. The other two examples here, they lie under category number 2, which is software attack surface. So here we talk about the software that's exposed, and the attacker can use that to attack the system. Or human attack error, or human attack surface. So if, for example, someone who is very smart and tries to share some of his own information on social media, or simply, tell someone else his username and password, or her username and password. Or a person who's actually inside the network and he can use his credentials, which is legitimate, to attack the system or to facilitate an attack to the system. And that sometimes happened, and it happened before during the blockade when they found some people, insider people, they actually, kind of facilitated the attack. So that's a human attack surface. So that's what we mean by attack surface. Attack trees are a logical way of performing the attack. So usually the attacker takes the approach of divide and conquer to try to attack a system. So he says, okay, I want to attack the Pentagon, for example. So attacking the Pentagon is like a big objective. It's very hard. So I need to break down this objective into smaller sub-objectives. These sub-objectives are grouped together, or they can happen either way. So you can, if you achieve one of these objectives, then you have achieved the bigger objective. So what I mean is, attack tree may have or and branches to exist at the same time. So it's a branching hierarchical data structure that presents or represents a set of potential techniques for exploiting these security vulnerability. And usually what we do is that we divide the big objective into sub-objectives, and we divide the sub-objective into sub-objective until we get to the terminal nodes of the tree. The terminal nodes would be just very clear and precise steps or technique, like for example, crypto analysis, like for example, sniffing the password. Sniff the password of someone who's really sending his or her password over the network with no encryption, something like that. So try to sniff the password for a certain legitimate user or something like that. So the terminal nodes of that tree would be, specific, precise steps or techniques that can be performed to achieve the original objective. So this is how it looks like. So this is an example of an attack tree for attacking a bank account compromise. So this big objective can be, divided into these smaller sub-objectives. So either we take the user credential compromise, or we do some injection of commands to get some. This would be using active attacks. In that case, we play as a man-in-the-middle attack, and we try to send some information to the user to impersonate, for example, the bank, or impersonate other banker, مثلا. And using this man-in-the-middle attack, we can get the information that we want to attack that bank account. Okay, or by using traffic analysis, or by using security policy violation. Like for example, if the person is having a password which is 123456, something like that. If the person is violating the security policy, and so on. So the big objective is divided into smaller sub-objectives, and as you can see, the terminal nodes are always precise techniques and steps that can be performed in order to achieve the big objective that we are trying to do. Okay. So user credential compromise, we can use brute force. We'll talk more about the brute force techniques, of course, as we go along. Or if the person is using a smart card, we can do some technique to perform smart card analyzers, and we can get the information of the smart card of the user, and based on that we can achieve the objective. Okay, so that's what we mean by attack tree. So it's a way for the attacker to perform the attack using divide and conquer technique. Okay. A network security models. So the security model, actually the security model summarizes and visualizes a group of techniques and services that can work hand in hand, okay, to realize a certain scenario or a network or a system. So for example, we have the very common two security models. We have the network security model, and we have the intrusion detection, or we have the information security model that we will see in the next slide. So for network security model, we talk about a sender who actually, performs some kind of confidentiality or performs some encipherment here, and then the secure message. Of course, this is the entire sender. So this is on one machine. So this is the sender on one machine. So the sender sends the data or his information through some encipherment that will be converted to a secure message. And this secure message will be transferred over a channel, whether this channel is wireless channel, is wired channel, whatever. So this, while the data is transferring over the channel, of course, the opponent can, or the attacker can see everything on this channel. You don't have any control that the attacker or the opponent can actually expose and see this message. But the idea is that if that attacker finds or sees a secure message which is already encrypted, he or she will not be able to extract anything out of it. That's the hope. And of course, on the other side, we have the recipient machine, which performs the reverse operation. So that network security model for us, is a very common model that describes the a network scenario and how we can use a confidentiality service over a communication network. Of course, this scenario very often it includes also a third party arbitrator or a server that acts as a security certificate authority, certificate authority or a third party that can be used to notarize the sending and the reception, as we said, for non-repudiation. It can be used to distribute the keys, as we will see later. It can be like a normal server that distributes the keys. But more often than not, we have some third party that facilitates this communication end to end and kind of, notarize all the sending and the reception of the data on both sides. Okay, so that's a network security model, of course, which is also very important, which is a network access security model. For a network access security model, this is used for intrusion detection. So this gatekeeper is some kind of a firewall or intrusion detection system, intrusion detection system, IDS. So this IDS system can facilitate certain types of access to a network system or a resource of some sort, whether this is a server or this is like some kind of a database or something like this. Okay, so if a human, if an attacker tries to access the system through the gatekeeper should be able to detect that this is an intrusion. Otherwise, if this is a legitimate access, the gatekeeper will pass it through. Okay, so that's a network access security model. It organizes this model, again, summarizes the techniques required to organize the access to an information system or a network resource. واضح كده؟ Any questions? Of course, unwanted, we're not gonna cover this in any way in our course, by the way. So this talks about the vulnerability or the unwanted access when it comes to intrusions and viruses and so on. So this is part of information security it does not involve any network access. So the placement in computer system of logic that exploits vulnerability in the system and that can affect application programs. So that talks about whether a software or a network protocol or a database in a server that we can hack in one server or machine. So that's what we mean by unwanted access. So any illegitimate access to the system, once we pass the gatekeeper, for us, for network security guys, خلاص, our job is done. Once we pass the gatekeeper, our job is done. But if you pass, you can actually have illegitimate or unwanted access to the server and insert some Trojans or insert some viruses and so on. So that's another story. So we'll not cover this part. So as we have discussed in this chapter, there are very common standard bodies. We have the NIST, and in the NIST we have FIBS, and FIBS is the subgroup under NIST, which is concerned with security recommendations and standards. And we have the ISOC. ISOC has again the subgroup of IETF. So IETF is concerned with the network security protocols. So you can say that this is part one of the book, because we are in part 0 now. Until now, we are in part 0. So part one of the book, we will talk a lot about the NIST standards. Okay, so NIST here is responsible for standardizing the security mechanisms. Okay, the security mechanisms. And the ISOC IETF, so this is FIBS, and this is IETF. So ISOC IETF is responsible for standardizing the network security protocols. Okay. And of course, in addition to these, we also talked about a third one. Anyone remembers what is the third one? A third standard organization. We talked about ISO, yes. We talked about ISO, صح. We talked about ISO, yes. So that's a third one, which is more. Mhm, mhm. Right. تمام. Okay. That's a good comment. Okay. That's a good comment. But I think when you get to work with security protocols over networks, you have to kind of come across ISOC IETF at some point. But I agree with you. Maybe ISO. Yes. Yes. Exactly. 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 Okay. So that's kind of a summary of chapter one. And there we talked about some definitions, examples, and concepts. What's computer security, what communication security is. We talked about passive security attacks, whether passive or active. We talked about security services and mechanisms. We talked about how to map security service to mechanisms, and then we talked about models for security, whether it's a network security model or a network access security model. We talked about also attack services, and we talked about attack trees. So that's kind of a full picture of most of the definitions that we will use in the course. Starting from chapter 2, we will get to specific techniques that we will commonly use in the course, in assignments, and later on for those of you who want to pursue some network security related issues. So in chapter 2 starts part 1. The book is divided into part 0, part 1, and part 2, and part 3. So part 1 here starts with the chapter 2, which talks about symmetric encryption and message confidentiality. So we'll start this chapter today, inshallah, and then we'll continue next time. So that's a simplified network security model for symmetric encryption. So as we have discussed, the network security model describes the interaction of the techniques or the security service and mechanism for a particular scenario. Here, what we are concerned with is to perform symmetric encryption. By symmetric encryption here, we mean that the sender will have a plain text input. This plain text input will pass through an encryption algorithm. This encryption algorithm can take different forms. We'll talk about the different possibilities, whether DES, triple DES, and AES and whatnot, and we'll talk about the differences between each one of them. For symmetric key encryption, symmetric here refers to the fact that the key is shared between the sender and the receiver. And that's a very important property for symmetric key encryption, that the key has to be shared. And of course, that sometimes causes some issue because the way that you share the key on both sides might actually expose the key. And that's, in many cases, it has to be done by a third party server like Kerberos server or something like this, as we will talk about in the next chapter or maybe the chapter after this. And this server will be responsible for distributing these shared keys to the senders and receivers. So we will talk about security encryption algorithms today. And then we have the transmitted ciphertext. The transmitted ciphertext, which is the output of the encryption algorithm, will be transferred as plain text to the other side, to the receiver. And during that process, the opponent can, in fact, get the ciphertext. So the minimum piece of information that the opponent or the attacker has is the ciphertext. You have to assume that the attacker always knows the ciphertext, but whether using this ciphertext the attacker can reverse engineer and get to the plain text, and more importantly, get to the shared key. That's what we don't want to happen. So once we reach to the other side, the decryption algorithm will perform the reverse operation by decryption or decrypting the ciphertext into a plain text, which can be consumed by the application. So we will perform, by the way, for assignment 2, we will perform this end to end as part of assignment 2 using like plain code. So you'll be able to program different security algorithms here, whether DES or triple DES or AES and something like that. And this will be a wireless channel, just a very simple error probability channel, okay? And you will see the effect of this wireless channel on the process of encryption and decryption. That's part of assignment 2 that we will have to post very soon, inshallah. Okay, so that's a very simple network security model that describes this scenario of symmetric key encryption. طبعا, there are no requirements for secure use of symmetric encryption. There is a requirement that the encryption algorithm has to be strong. And that's a fluffy word, yani strong. The strong here means that just by having a cipher text, of course, it's impossible to get to the key or to the plain text except using some brute force techniques. Okay, so that's one level of strength, but that's not enough because, for example, the simplest form, there is a simplest form of security algorithm, which is very common. It's called VERNAM encryption algorithm. This VERNAM, what it does is that it says, okay, so I will take the input plain text, okay, I will XOR it with the key, and I will perform the ciphertext. That's it. So plain text XORed with the key to get the ciphertext. Okay. As simple as this algorithm is, this type of algorithm is actually proven, and it proves to be protective against the case that you have a copy of the ciphertext. If you have a copy of the ciphertext, you can never get to the key using the ciphertext just by doing the XOR, simple operation, XOR. Okay, so so this type of security algorithms or encryption algorithms is proof against the ciphertext only attacks. However, if you have the ciphertext 1 and plain text 1, just one plain text, you can say ciphertext 1 XORed with the plain text 1, the result will be the key. Once you get the key, خلاص, that's it. Okay, so although this type of algorithms is proof against the ciphertext only attack, but it's not proof against different types of attacks. Of course, the proof for this, by the way, is not as easy as you think. The proof that it's very protective against the ciphertext only attack based on information theory, but it is there. There is mathematical proof that this VERNAM algorithm is actually strong if the only information that the attacker has is the ciphertext. But we'll see that, of course, this is a very simplistic assumption, and in many cases we have, or the attacker has more than just the ciphertext. So right. So if this one-time pad process has very random input that has no way of the attacker trying to guess that input, then the Vernam algorithm will work just fine, because as long as the attacker does not have an example of a plain text that corresponds to a ciphertext, just one, okay, everything will be fine. But in many cases, when we communicate, for example, in English. Let's say we communicate in English, or we communicate using a specific network protocol. So the attacker makes certain assumptions. Since we communicate in English, so the first part of the communication will very commonly include something like hi, or include something like salam alaikum, or include something like this, right? So the attacker can make certain assumptions that will help him or her to get a plain text that corresponds to the ciphertext, and we'll talk about this in more details. In that case, the Vernam algorithm will become useless, will become very useless. But for one-time pad process, if there is no way you can guess the input, then it is attack proof. I mean, the Vernam algorithm is attack proof. Another example is that when you communicate using HTTP, so the attacker knows that most probably, even if you are using HTTPS, the attacker knows that in the beginning of the communication, HTTP header will have certain content that has to happen in the beginning of the communication. Okay, so the attacker can make certain assumptions that will allow him or her to get some plain text that corresponds to the ciphertext, and in that case, certain types of algorithm will be almost useless. So strong algorithm here means that even if the attacker has ciphertext 1 and plain text 1, ciphertext 2, plain text 2, ciphertext 3, plain text 3, something like that. Okay, so even if the attacker has all of this, he or she will not be able to guess what the key is. And still, it's very hard, and in many cases, the attacker will resort into using brute force techniques to get the key. But again, if you have the more information that you have, the more you can reduce the amount of combinations that you have to do in order to guess the key, and in that case, you will spend less amount of time to attack the communication. So we will talk about the different categories of attacks based on what the attacker has in terms of information. The security of symmetric encryption depends on the secrecy of the key. And what that means is that always remember that the security algorithm, the encryption algorithm itself, the algorithm itself is public. It's actually published. Okay, and we will talk about the structure of the DES and triple DES and AES. The algorithm itself is public. Okay, so it's known. So the only thing that strengthens this algorithm is the secrecy of the key. Okay, the encryption algorithm needs to be strong in the sense that even if you have more information, it's still difficult for you to guess what the key is. But once you guess the key, halas, everything is known to the attacker, because the security algorithm itself is public. So the attacker can, in fact, act easily as man in the middle and represent or impersonate the sender for the receiver, and impersonate the receiver for the sender, and get all the information that he or she wants. Okay? So the secrecy of the key is the most important part of that process. Why do we make the encryption algorithm public? But what the encryption algorithm itself is actually public. So let's make it a trade secret or some kind of a secret algorithm, okay, and just deal with it as such. Sorry. That's a good point. Yes, that's true. But also by publishing it and everyone knows it, it will be known by everyone, not just the sender and the receiver. Everyone over the internet knows exactly what the encryption algorithm, how this algorithm is structured, what are the blocks, as we will see, and so on. Okay, but this makes it feasible for being أول حاجة it makes it very widespread. It makes its use public. معناها everyone can use it. If it's secret, معناها it will be proprietary. Proprietary means that it's used by a single organization or two organizations. The organizations that share the secret are the only ones who can use that encryption algorithm, right? So by making it public, it would be widely used, and that's why it's a standard. Standard means what? Standard means that it's agreed upon internationally. Everyone agrees that these standards are, are the way they are, and they can use it as such. So, not only that, manufacturers, they can manufacture some hardware to optimize the encryption algorithm. They can perform some chips that optimize the operation of encryption and decryption, because it's public, and they know that once they do, or once they manufacture this hardware, again it will be used by everyone around the world. So they are not making this chip again proprietary and it's exclusive used by one or two organizations. Everyone on the internet can actually use it. ماشي كده? So these chips are also widely available and incorporated into number of products, and that's why like on our cell phone, you might find that the encryption chips are manufactured by a certain organization or a certain vendor, and this chip can be, in fact, embedded or used or integrated in iPhones, in Galaxy phones, in all types of phones. Okay, this could be the case because, again, it's a standard encryption technique, so it can be used by everyone. Okay, but of course, the challenge here is that despite the fact that the algorithm is public, it has to be strong in the sense that it has to be proof against the different types of attacks, as we will see. And this is, I think, this is one of the drawbacks of this course, is that يعني, or the book that we are using, that it does not go deep into information theory about why certain combinations of XORs, transformation and substitution, why is this proof against certain attacks. So that requires information theoretic course, which we will not get to, unfortunately. So I will talk about the security or the encryption algorithms in terms of structure, but we will not get into the information theoretic background behind why this algorithm is يعني proof against certain attacks. And I will explain what I mean يعني later, inshallah. So the cryptographic systems are generically classified along these three independent dimensions. So the type of operation used for transforming plain text to ciphertext, in many cases, we resort to one of these three operations. So substitution. By substitution here, we mean that we have sort of a, let me explain. So we have the input text, okay, and we have sort of a lookup table, okay, and the substitution here talks about the fact that we take each part of that input text and then from this table we convert it to an output text. Okay, that's what we mean by substitution. Okay, the transposition is, in fact, we don't actually convert or transform the text. Yet what we do is that we take certain parts of the input text and then we shuffle it. We change its location, but we don't transform it to something else. Okay, so most of the encryption algorithms that we will talk about will perform one of these two operations. Of course, the third one, product systems, is nothing but a combination of substitution and transposition. That's it. But you will have to do that repeatedly, okay? And the more steps you use the substitution and transposition, the stronger the algorithm will be, okay? To be proof against any kind of reverse engineering, okay? So the second category is the number of keys used. Very commonly, if we use a single key which is shared between the sender and the receiver, we call this symmetric key encryption. And symmetric key encryption is used in many ways for confidentiality. If we have two keys, one public and one private, okay, so which is the second type here, we talk about asymmetric key encryption, and in that case we use the public key for encryption and the private key for decryption, or the other way around. Sometimes we talk about when to do either of these. The third one is the way in which the plain text is processed. So we have, in this case, or in this categorization, we either have block cipher or stream cipher. By block cipher here, we mean that we divide. Let me just. By block cipher here, we mean that we take the input text, this input text, we divide it. Let's say this is an image, and just to make it relevant to assignment 2. So let's say that this input text is an image, big image. And then we will divide it into blocks. So this is block 0, block 1, and so on. Okay? And then we take block 0, we input this block 0 into the encryption algorithm. Okay? And then we perform the ciphertext. Ciphertext طبعا 0. And then we do this for each of these blocks. And then we will talk about the operation modes later on. Sometimes we have to shuffle the ciphertext between these blocks and so on, but that's another story. So that's what we mean by block ciphers. Some of the properties of this block cipher, if there is the ciphertext will be transferred over the network. The ciphertext is exposed if it's altered by any means. Okay, you can never get back to the block 0, even if you have the key. If it's altered, if it's modified by the attacker in any way, which affects the data integrity, sometimes it's changed by the channel itself. The channel has some probability of error. So in that case, if you change the ciphertext only 1 bit, even 1 bit, okay, if you try to go back to the plain text or to the input text, it's very difficult. You will see that the input text has changed a lot. That's based on the properties of the block cipher, and that's one of the disadvantages. Although block ciphers are much stronger, so block ciphers here are usually much stronger compared to stream ciphers. Okay, we will talk about some examples for block ciphers, including DES, triple DES, and AES, and we will talk about one example for stream ciphers, which is what we call RC4. For stream ciphers, it's a bit different. So what we do here is that we have an input text. So this is the input text, and we have like sort of a key. This is the key. Okay, so from the key we have to find, so the algorithm itself converts or transforms the key into another text, okay? And then all what you need to do is just simple XOR to generate the ciphertext. And that can be done in one shot. So you don't have to transfer the input text into blocks. So you just convert the key using certain algorithm to another text that will be XOR to the ciphertext. Of course, if the ciphertext in that case is altered, you will see that this stream ciphers are prone, or sorry, they are really prone against the modification attack or against the types of attacks that modifies the ciphertext. Okay, we'll do that as part of the assignment too. Okay, so these are the categorization of these encryption algorithm. Type. So the types of attacks based on what the attacker knows. The strongest or the minimum amount of knowledge for the attacker is the ciphertext, as we said, because this ciphertext is transmitted over the network as plain text. So the attacker knows at minimum the ciphertext. Okay. So the attacker knows the encryption algorithm because it's public, and he or she knows the ciphertext. Okay. In many cases, the attacker in that case, in that type of attacks, resorts into what we call brute force attack, which means that based on the based on this ciphertext, I need to guess what the key is. So we have the encryption algorithm, which is a big function of the input text or the plain text and the key. Okay, so from the ciphertext, I need to guess what the key is, and the only information that I have is actually the ciphertext. That's the only thing I have. I have only CT1, CT2, and so on. I have this. Okay. So in that case, what we can do is that we take that key. If we know the length of that key, let's say the length of the key is capital K. So what are the different combinations? What is the maximum combinations I can have to guess what the actual key is if I have the length of the key as K? What is the length, or what are the maximum number of combinations I have to guess what the key is if I use brute force attack or brute force technique? K, 2 to the power K. Yes. So because remember, at the end of the day, the key is binary, right? Binary means that each bit takes two states, either 0 or 1. So all I need to do is that the length of the key is capital K, sorry. So all I need to do is just to say, okay, so it's 0, 0, 0, 1, 1, 1, 1, 1, whatever, okay? And then I will do the different permutations or the different combinations of zeros and ones to try to guess what the key is. So that's brute force. Of course, this is the maximum. Go ahead. Yes, I was gonna get to that. I was gonna get to that. So this is the maximum. This is the maximum number of combinations, assuming. Sorry, I'm stupid and I don't perform any level of intelligence, and I do the different combinations blindly. The maximum number of combinations is 2 to the power k. However, in many cases, because guessing the key is actually a random process, and the key is actually for us is a random variable. And this random variable, assuming that this random variable, this key, takes certain combinations with the same probability. Let's assume that the key has uniform distribution. So you have 2 to the power k combinations, right? So this is a random variable. If you have from the first combination all the way to 2 to the power k combination, okay? So this is the maximum combination, maximum number of combinations I have. But what is the average? The average is, of course, half, right? So usually it's 2 to the power k minus 1. So in many cases, I will perform 2 to the power k minus 1 guesses to get to the key, plus or minus on average, okay? So this is this is the minimum, okay? And of course, in that case, as you can see, the longer the key, the stronger the algorithm is, or the stronger the encryption is, right? That's no brainer. So we can see that. Type. And as you can see, by the way, the Vernam, again, we go back to the Vernam algorithm, okay? It's actually very good. It works very good for these types of attacks. There's no problem with it, although as simple as it is, because the Vernam, what it does is that it says ciphertext is actually plain text XORed with the key. That's it. Very, very simple. So if you have CT1 guessing the key without knowing the plain text, you will have again to resort to the brute force attack. But this is given the fact that, again, you do not have any information about what the plain text could look like. In many cases, 90% of the time, the attacker makes certain assumptions to know more information than just the ciphertext. أيوة مالك تفضل. طيب ما هو 2 to the which is 2 to the power k minus 1. Yes. Yeah, so the average number of steps you need to guess the key is usually 2 to the power k minus 1. The known text here assumes that the attacker not only knows the ciphertext, but he actually knows ciphertext 1 that corresponds to plain text 1, okay, or maybe multiple of these. And as I said, in many cases, that's easy. That's easy to guess, or that's easy to assume, because in all types of communications, the attacker knows that at the beginning of the communication, you have to exchange some headers, some network protocol headers. So he makes certain assumptions that these headers should contain this amount of data or these types of data. Based on that, he knows roughly what the cipher or what the plain text should look like. So at the beginning of the communication, he can sniff some ciphertext, knowing the fact that this ciphertext in fact corresponds to a specific plain text. So that's a common type of attacks, and of course, in that case, the number of combinations get lower and lower. So definitely, brute force attacks will not be efficient in that case, and you can use this information to have less number of combinations to guess what the key is. The chosen plain text and the chosen ciphertext, the difference between known plain text and chosen plain text here is the fact that the attacker is in fact performing man-in-the-middle attack. So in other words, the attacker can control what the plain text will look like. So it's something like this. So let me just so the attacker would be in the middle, and you have the sender and you have the receiver. Okay, so in that case, the attacker impersonates the receiver to the sender and impersonates the sender to the receiver. Okay, so the attacker can send some chosen plain text to the sender and ask the sender, okay, so please encrypt this. Okay, so he knows that the sender will encrypt this and send it back to him. So in that case, he can control the input text. Not only know what the input text is, he can control. So in that case, he can choose the plain text in such a way that he allows him to get more information about the key. Okay. Of course, he can do the same thing with the decryption. So he can send a cipher text to the receiver to ask the receiver to decrypt, assuming that he has access to the decrypted text. Okay, so in that case, the attacker performs man-in-the-middle attack that allows him to get access to the sender and access to the receiver. So in that case, you can easily get the key of any communication between the sender and the receiver by using the chosen plain text attack or chosen ciphertext attack. Or, of course, chosen text here means that it's a combination of the plain text and the ciphertext. So you can control both. Okay, you can control the plain text and you can control the ciphertext, and in that case, you can get multiple combinations of plain text and ciphertext, and from that you can attack the communication easily and guess what the key is. Okay. So any question so far? So that's what we mean by yeah. Go ahead. Yeah. Hopefully you have anything better than this. If you have better than this, you are welcome to do it. But what I'm saying is that using the brute force attack, there is no encryption algorithm on Earth that's completely proven, completely proof from the attack. Okay, you cannot protect any encryption algorithm 100% because the worst case is that you use brute force. Okay, but of course, smart attackers, they use different techniques other than brute force, طبعا. So they use the different smart techniques that will allow them to get to the key using less number of guesses. Okay. So so we know that the encryption algorithms cannot be 100% proof. So what do we do? So what we try to do really is to try to make the cost of breaking the ciphertext exceeds the value of the encrypted information. Because we know that the attacker can always attack, can always use brute force to get to the key. Okay, so just imagine that I'm making some transaction with the bank which is worth, let's say, $2,000. But in order for the attacker to break that type of transaction, he or she has to get a big server to perform the brute force 2 to the power k, and k here is 128 bits. So good luck. You have to perform billions and billions of operations, which requires a big server, which costs $3,000. So what's the point? I'm actually I'm using a $3,000 server to break $2,000 or less operation. Okay, and not only that, the time required to break the cipher exceeds the useful lifetime, which means that by the time you break the communication, actually, in fact, the key will have changed. And that's what happens in many communication systems, is that the key distribution server has to distribute these keys regularly. So every few minutes or every 1 hour or something, the key has to change. Okay, so of course, in some encryption algorithm, you can take 1 hour to actually break the communication or less. We'll see that, but hopefully within this 1 hour, by the time you get to breaking the communication, the key will have changed. So you have to go back from the beginning and use brute force again and so on. So you will go into loop and you will never be able to break the communication. So a strong encryption algorithm should, in fact, make the cost, because the cost will not be infinity. Definitely, the cost will not be infinity. The cost is limited, but you should make the cost okay, more than the value of the communication itself, okay, or the lifetime of the key less than the duration of time that the attacker can use to break the communication. Okay. طبعا example of an easy algorithm, we all know the Caesar cipher. The Caesar cipher is one of the encryption algorithms that used to be used by the Roman, and it's simply like a substitution cipher that shifts the characters, and actually the key is nothing but a number, يعني 6 مثلا. So what you do is that you take the plain text. This is the plain text, and the key is 6. So you have the alphabet. The alphabet is A all the way to Z, which is 26. And all you need to do is just to shift one letter from here. You shift it. You see this letter in this table, in this lookup table, and then you shift 6 places, and then you get this in E, and put it in the location of that letter. That's all what you need to do. It's very, very simple. So you just need to do substitution based on a lookup table based on the key, and the key here is the number of shifts between the plain text and what the ciphertext should be. Okay, and of course all the operations are not 26. So if you shift 26 and it becomes مثلا 30 or something, then you have to go back from the beginning and circulate. Is this clear, or I need to show an example about this? I think it's clear, yeah, it's straightforward, yeah. Okay. طيب. So brute force attacks, it involves trying every possible key until an intelligible translation of the cipher into plain text is obtained. Of course, here the assumption is that the attacker needs to have an assumption, even only by plain text. The attacker needs to have an assumption that, for example, the communication is in English. Okay, so if I take the ciphertext and I do the decryption using one of the standard decryption techniques like this or triple this, and I get to using a certain طبعا key that I guess, okay, I get to a plain text. How would I know that this is the right plain text? I have to have an assumption. In that case, I have to have an assumption that we communicate in English. So yeah, so that looks like a grammatically correct sentence in English. So I stop. In that case, I stop. So we'll see an example of this. So on average, half of all the possible keys must be tried to achieve that success, which is what we have discussed, 2 to the power k minus 1. So unless known plain text, okay, is provided, the analyst must be able to recognize the plain text as plain text. So you have to have, this is what I mean by the fact that you have to have certain assumptions by how the plain text should look like, whether it's English or whether it's HTTP header. So yeah, that looks like an HTTP header or something like this. To supplement the brute force approach, then some degrees of knowledge needs to be known. Whether some expected plain text needs to be expected. يعني مثلا I know that in the beginning of the communication they need to exchange specific headers, so I have to guess some plain text, and I know the ciphertext that corresponds to this plain text, in which case I can use this knowledge to reduce the number of combinations for guessing the key and so on. أحط الexample. Basically what happens is that if the attacker has the ciphertext, okay, so the attacker can guess the key. So this is key 0, and then from the key and the ciphertext we should have the algorithm, the decryption algorithm, okay, and then we get the plain text. If that key is correct, the plain text will have proper structure, okay, like for example my name is Amr. Okay, if I try an incorrect key, ki, it's incorrect, I will get any garbage here. Okay, I will get any garbage. So in that case, I will assume that that's not the right key, because the structure of the plain text does not look correct. So that's what we mean by the brute force. Okay, I insert some example here. So attack. So we have to have certain assumption on how the plain text should look like. Right. So Nest specifies in one of its recommendation what we call the FISL, or the fiscal encryption and decryption. Okay. So the FISL structure is one of the very, very important ingredients for all types of encryption algorithms. It's actually the main building block for this and triple this, as we will see. And this FISL structure is based on 16, so from round 1 to round 16, okay? So we have 16 rounds. Each round, we divide the text itself. The text, by the way, very commonly is 64 bits, okay? The text is 64 bits. So we divide it into 32, which is the right element, and 32, which is the left element. Okay? So in that case, the right element, this right element of I equals to the left element of I minus 1, okay, which is this one, XORed with the function of K of I and the right element of I minus 1. Right? صح? Are you following this? So we take the right element, we perform function F. Function F takes the key, which is key 1, and the right element of RE0, perform this function, and then the output will be XORed with the left element I minus 1. And the left element of I equals, very simply, R element of I minus 1. Okay? So these two equations, in fact, summarize the FISL structure. Okay? And that's very good. So we'll talk about why this is very good. This is very good to analyze and to be able to represent the encryption algorithm in simple equations like this. Okay, and of course, by having the I index, this means that we can recursively perform this operation on 16 different rounds. Okay, and that's very strong. So by increasing the number of rounds, we make the algorithm stronger and stronger, but we also make the complexity higher and higher, right? So the trade-off, based on what the Nest recommends, is to have 16 rounds of these types of operation. Okay, and then the last round, which is the 17th round, we do just simple swapping, which means that REN equals to left E of n minus 1, and left EN equals to REN minus 1. That's it. So it's a simple swapping. Okay. What we will not answer in this course is using information theory. Why, when we do it this way, okay, we think that this is very, attack proof. Okay, so in order for us to say that doing the encryption and decryption this way will make the fizzle structure very proof against any types of attacks. In order for us to answer this question, we need to study basically information theory, which we will not get to as part of this course. So this is the fizzle structure, and as you can see here, the decryption is the reverse operation starting from here. Okay, so starting from here, we get the cipher text, and we get, of course, the RD0, which is LE16 because of the swapping that we did, and then we do the reverse operation. Okay. Any question here? So the fizzle structure is type. Now, why do we have K1, K2, K3, and K4, and all the way to K16? So, as we all know, that we are supposed to have one key, right? So we have each encryption algorithm would contain or would include what we call sub-key generation algorithm. Sub-key generation algorithm. So we will talk about some examples of this sub-key generation algorithm. Basically, we take one key as input, so we have one key. Then from this key, we generate all these keys. Okay, using what we call the sub-key generation algorithm. Okay, so the encryption algorithm is public. Sub-key generation algorithm is also public. Okay, but the purpose of this sub-key generation algorithm, again, is to make the encryption algorithm strong by performing multiple rounds with different keys. By doing this multiple rounds, multiple repeated rounds with different key every time, we make the encryption algorithm stronger and stronger. So this fizzle structure is the basic building block for DES and triple DES, which is standardized by NIST. Any questions so far? Can we get back from subkeys to? You can, and because the subkey generation algorithm is public. So if you know all the K1 all the way to K16, I guess it's a one-to-one operation. So you can sort of get the key. It's actually a good question. I think you have to get one key only. If you get one key only, you can perform the reverse operation, because again unlike these rounds, the sub-key generation algorithm is straightforward. We will see how we can do it. It's based only on simple permutation. But actually I have to check this. The permutation, it could be irreversible. I have to look at that. The permutation could be irreversible. We will talk about some example for the sub-key generation algorithm. It's basically based on some permutation. So what you do is that you have to change the location of some bits, okay? And just a simple transposition using certain permutation, and that it generates key 1 and key 2 and key 3 and all the way to K16. But you don't perform any complicated functions like مثلا this function. You don't actually do. We'll see. We don't do complicated operations. So the permutation might in fact be reversible in certain extent. But we will check that when we get to this. This is actually a good question. Here we have function f here, this f function. It also the more complicated this function is, again, the stronger the encryption algorithm will be. In fact, NIST does not dictate a certain function. It says that you have to have a function, but يعني it's up to you بقى to design what complicated function you want based on the complexity that you want. But this structure needs to look this way in order to make the algorithm strong. That's what we did when we mapped the fizzle structure into two equations. So I can easily convert and map the fizzle structure. So it looks very complicated. As you can see, it looks very complicated, multiple rounds, and. But when we break it down to two equations, it becomes very simple to understand, right? And that's good. What is that? As we said before, the structure looks very complicated, right? But we said that we can convert this fizzle structure into very simple two equations, which says that RE I equals to LE of I minus 1, which is this one, okay, which is XORed with the function of the RE of I minus 1 and KI, right? And then LE of I equals to RE of I minus 1. These are very simple two equations, right? Despite the complexity and the sophistication of the algorithm, when we convert it this way, we can give these equations to information theoreticians and say, okay, so just go and analyze the boundaries and the strength of these information or equations from information theory point of view. Okay, then they can make certain assumptions on the RE elements, what is the distribution, and deal with some statistical analysis to say, okay, so based on Shannon theory and stuff like that, this is very strong in terms of being proof against attacks. Okay. Well, you will see that in assignment 2, the implementation of this fizzle structure as part of DES and triple DES, especially when we get to defining what this function looks like, you will see that you have to work on the bit level. You have to do lots of shift left, shift right, and when you deal with bit level operations, it's optimized for hardware, not for software. In software you can do that, but if you do that millions of times, it's very slow. But when you do that using hardware, it's very fast, right? So the main issue with this fizzle structure and with this as a result is the fact that it deals with bit level operations, which requires some shift left, shift right operations and some substitution on the bit level. And that will be much more optimized if we talk about hardware implementation as opposed to software implementation. And you will see that in the assignments. In fact, with AES, we don't deal with bit level operations. We deal with matrix multiplications and matrix manipulation. We'll see that. So matrix multiplications, we know how to do this very efficiently. And in fact, assignment 2 will be in MATLAB. MATLAB in particular is extremely efficient when it comes to matrix operations. So you will see that AES has maybe 1 over 100 the complexity of DES and triple DES. And in fact, it's proven from information theory perspective that AES has the same security level and the security strength of DES, of actually triple DES, when we talk about the same key size. So for the same key size, AES has the same security level, if not even better. And in terms of complexity, it's 1/100 maybe. It takes much less amount of time. So there are, for the fizzle structure, it actually, there are some factors that affect the performance of this fizzle structure. Of course, in order to get down to the boundaries of how this fizzle structure is proof against attacks and some stuff like that, we have to study information theory in details. But here we can talk about some high-level parameters that affect the performance of this fizzle structure. One thing is the block size, right? So block size, the larger the block size is, means greater security, because again, more substitution and transposition for a bigger block makes the encryption algorithm more proof against attacks. So the bigger the block size, the better. Also, the key size clearly affects the performance or the strength of this encryption algorithm. Key size is because, again, the key length affects the amount of, or the number of guesses that you have to do in order to get to the key. But also the number of rounds, as we said, the number of rounds that we perform affects also the performance. But the problem here is that the number of rounds affect the performance in terms of security level and strength, but it also affects the complexity. And in many cases, we have to really look for complexity when it comes to designing these encryption algorithms. It's very, very important. The sub-key generation algorithm also, and that kind of answers your question. Again, the more complicated this sub-key generation algorithm should be or will be, again, the more difficult we can guess the actual key from the keys, and in that case, there is no correlation between K1, K2, K3, K4, all the way to K16 and the original key. So there's no actual correlation between them, in which case it will be hard to guess the actual key. The round function, which is function F, as we said, or attack proof. So this round function here refers to function F. One important factor is it a software, is it a fast software encryption and decryption algorithm? بمعنى, can I actually implement this encryption algorithm in software and it would be fast? As we will see in the assignment, is that DES and triple DES are very, very complicated. That in many cases you need to have hardware. So we will see the software implementation of DES and triple DES. It's very complicated and it takes a huge amount of time. So we'll see in assignment 2, the amount of time that you need to encrypt an image using software implementation for DES and triple DES is huge. And the main issue with this is the fact that the fizzle structure deals with the bit level. It deals with bits. And we will talk about this in more details when we get to AES. For AES, we will see that we will deal with matrix operations. So with matrix operations, we can do that very efficiently. But dealing with bits dictates or kind of forces the hardware implementation. Okay, and that's why for DES and triple DES, in many cases, people resort to chips, actual chips, to use these encryption algorithms in the systems that we have nowadays. Okay, another interesting factor here is the ease of analysis, and that's a very interesting point now. Is that the algorithm, it should be strong, but it should be easy to explain. يعني شوف, it's two conflicting objectives. So the algorithm needs to be, on one hand, very strong, which means it needs to be sophisticated, but at the same time, it needs to be simple to explain. And that's what we do. Because the information theoreticians, they can take these equations that we just put down, they can take it and perform some kind of boundaries on how this physical structure is proof against attacks and what is the boundaries in terms of security strength and so on and so forth. They can do that, okay, because the physical structure can be explained easily using these simple equations. So despite the fact that the security algorithm needs to be strong and sophisticated, it needs to also be easy to explain, which is kind of interesting to have both factors in place. واضح كده؟ Any question يا شباب؟ Go ahead. No. That's not what I mean. ماشي كده؟ So these are the main block ciphers that we talk about in this course. So we'll talk about the data encryption standards and the triple data encryption standards, or triple DES. So triple DES is nothing but repeating DES 3 times. We'll see how this is done. It's very easy. But why do we have triple DES? Since DES exists, the idea is that, again, there's that the strength of this security technique is based on the key length. Unfortunately, DES itself is designed with a small key length, which is 56 bits only, and it's like using 56 bits for the key. We need 2 to the power 55 operations if we do brute force attack. Okay, so you can do this using a powerful machine. You can do this maybe in 1 hour or less. You can perform this. So they try to strengthen the DES by having triple DES, which uses 3 times the key size. It uses 3 times the key size. AES, it's totally different. It's fundamentally different. It's not based on the bit level operations. It's based on byte level manipulation, and it's based on matrix multiplication, which is totally different. Okay. So these 3 standards, they constitute what we call the block cipher. So all these standards or encryption algorithms, they lie under the category of block ciphers. Okay. So let's take a 10-minute break, maybe, or maybe لسه المغرب لسه ما قدامش. Okay. So we'll continue for another 5 or 10 minutes, and then we'll break for 15 minutes or so for Maghrib. So this is most widely used encryption scheme, but that statement is not valid anymore, I would say. So the many people over the internet, they found some vulnerability, not vulnerability, by the way, in the algorithm itself. The main weakness for DES is actually the key size, which is 56 bits only. Okay, so using brute force attacks, you can really do brute force attack with reasonable amount of time and get to the key. Okay, so the algorithm itself is called DEA, or data encryption algorithm. So this algorithm uses a plain text of 64 bits. The key size is 56 bits in length. The structure itself contains inside it the fizzle structure, the fizzle network, for 16 rounds. However, as we will see, there is like minor modification or minor variation to the fizzle network or the fizzle structure. So we'll see that there are some envelopes that are designed around the Fizzle network to perform the data encryption algorithm. The concerns for the DES algorithm, the algorithm itself refers to the possibility that the crypto analysis is possible by exploiting the characteristics of the algorithm. That's actually not a disadvantage for the Fizz structure. The Fizz structure until today, no one was able to find a flaw or a discrepancy in this algorithm that can be exploited for attacks. The main issue with the Fizz structure or with the DES algorithm was actually the key. The key size is 56-bit key, and in that case, it's pretty small. Of course, in the past, the computational capabilities of any server or system was very low, and in that case, you need like some kind of a mainframe to perform 2 to the power 55 operations or something like that. But of course, nowadays you can do it with even a cell phone in 1 or 2 hours. And of course, the Nest also, they were actually visionary that we nowadays we talk about quantum proof and so on. So with quantum computation, we need to really provision for servers that they work much faster than the servers that we have nowadays. So that's why the concept of quantum proof security techniques have come into place, and many people, they are trying to make their security techniques quantum proof, and that requires different level of analysis than nowadays. So this is the structure of DES, and again, it looks complicated, but when you break it down, it's very simple. So in the middle here, we have the 16 rounds until here. So this is the Fizzle network. It's as is, okay? We did not do anything with this. So round 1 until round 16, and then the 32-bit swapping. So that's what we added here is only the initial permutation and the inverse permutation. So what we do is that we do the permutation here, we'll do initial permutation, and we do one final permutation, which is sort of a reverse. So this is what the initial permutation and inverse initial permutation look like. And of course, you don't have to memorize these permutations by any means, but this can give you some idea about the complexity of the algorithm, because we're talking about the bit level here. So bit number 0 goes to bit number whatever. So you have to do every single bit, you have to change. And usually dealing with bit level operations is very, very complex in software. And that's why in many cases, they resort to implementing this in hardware, okay? So this is key 1 and key 2, which is based on the sub-key generation technique or algorithm. And one thing we notice here is that here we have the key 64 bits, but we said that the key is 56 bits. So in fact, for 8 of these bits, 8 bits here are parity bits. So these are not used for encryption. These are parity bits which get generated initially from the 56 bits. They generate 8 parity bits, they add it to the key, and then they perform the operation. So I have to also say that the sub-key generation algorithm is nothing but permutation and then circulation and then permutation again. Okay, as we said, any encryption algorithm or sub-key generation algorithm, it does permutation and substitution. Permutation in terms of substitution and transposition or changing the bits, the bit location. So the permutation choice 1 here, this is how it looks like. Sorry, this is the initial permutation. Sorry, the permutation choice 1 here is not in this picture, but we call this permutation with contraction. So we go from 64 bits to 56 bits. Okay, and then for we do the circular shift. The circular shift is basically you shift the bits one location or two locations to the left or to the right or something like this. That's all what you need to do. And then you do another permutation, which again plays on the bit level. And this is another permutation with contraction too. So the permutation with contraction here produces 48 bits. So the key that you generate for each round is in fact 48 bits. So we go from 64 bits to 56 bits and then to 48 bits. So each of these permutations, we call it permutation with contraction. We compress the 64 bits to 56 bits or the 56 bits to 48 bits. Okay, and in the middle you have only circular shift. So that's basically, and I don't think, Lace, to answer your question, I don't think this is reversible. I don't think this is reversible because once you do permutation with contraction, it becomes irreversible. And actually, this is maybe the reason that they do it this way. Because from 48, if you want to go back to 64 bits, okay, you have multiple options, and in that case, you will not be able to guess it easily. You will not be able to reverse engineer it easily. I think, yeah. Okay. ماشي. So again, this is the sub key generation algorithm, which has an output of 16 key. Each key is 48 bits. Okay, and this key will be input to the round 1, round 2, all the way to round 16, and this way we perform the this encryption algorithm or the data encryption algorithm. Okay, again, the what you need to know here is the structure. You don't need to memorize, of course, all these permutations in any way. What you need to know is that you have an envelope of initial permutation and reversible or inverse initial permutation. And in the middle, you have the fuzzy structure, and the subkey algorithm or the subkey generation algorithm is the permutation, the circular shift, and permutation tool. That's all what you need to know in terms of the structure of this algorithm. From this step is that the permuted choice 1 is performed only one time. Huh? So it's performed at the beginning once, and then the remaining rounds or the remaining keys are generated just by circular shift and then permutation choice 2. So permutation choice 1 is done once, but permutation choice 2 is performed on every single key or subkey generated based on circular shift. Okay, so any questions? طيب, let's break here and يعني break for, let's say, 15 minutes for prayer, and then we'll come back, inshallah. Okay, so we're back to talk about the structure for this. As we can see, reflects here on the fact that for input to stage I, we have Ci-1 and Di-1, which constitute the output of the permutation choice 1, which compresses or contracts the 64 bits to 56 bits, so 28 and 28. And then we do the circular shifts based on 28 bits and 28 bits separately. And then these circular shifts will be an input to permutation choice 2, which again, it does some contraction to convert the here. So the input the input to that block is 56 bits, and the output here is 48 bits only. So these 48 bits will be XORed with the output from this stage. So so what we have in this dotted frame block here is what we call the F function, or the round function. So the F function is, as we said before, the Ri minus 1, or the right element, which is 32 bits. In order to perform an operation for this Ri minus 1, we need to convert it first from 32 bits to 48 bits. Okay, so we do that using permutation with expansion, which is the opposite of permutation with contraction. So here it's permutation with contraction, here it's permutation with expansion. Okay, so we convert 32 bits to 48 bits. Once we do this, we can perform just a simple XOR. So this is the Vernam cipher, the normal Vernam cipher, and then the output will be also 48 bits. Then we do what we call S box, or substitution box. This S box is nothing but a transformation, or a substitution for each 6 bits. We convert it into 4 bits. So we convert the output here to 6 bits at a time, which means that we have 6 bits times 8. Okay, each 6 bits will convert it to 4 bits by using like a lookup table. So this is a lookup table that has columns and rows. What we do is that we take each 6 bits, we use it to look up a value of 4 bits, and then we put these 4 bits here to represent the output. After we finish this, we do another permutation step, which is neutral in that case. This permutation step does not perform neither contraction nor expansion. So it's one-to-one permutation, and the output will be 32 bits, which will be XORed, as we said, for this round. So this is the F function. So the F function performs 3 or 4 operations. Permutation with expansion to convert 32 bits to 48 bits. Then we do XORing. Then we do S box. Then we do like the final permutation step to produce the 32-bit output. Okay, and we do this for every single round. This is, of course, the permutation with expansion, which again, you don't have to really memorize how it looks like or what kind of bits are permutated to which location, but this is how the permutation with expansion would look like. So in that case, the output has bigger size than the input. For contraction, the output will have less size than the input. Okay. Any question for the DES algorithm? So basically, the DES algorithm, because the key has 56 bits, the number of key combinations, or the number of guesses that we can do, is 2 to the power 56, which is this huge, number, which I cannot even describe or pronounce. But the time required, if we were to do 10 to the power 9 decryptions in 1 second, the time required will be 1 year. But that's what we used to have in the past, that we perform 10 to the power 9 operations every second, because the computational capability for the servers was not very sophisticated. But if we talk about 10 to the power 13, which is more of what we have nowadays, we can actually break this communication in 1 hour using, again, brute force attack. Assuming, of course, that the average number of guesses that we can do is half the 2 to the power 56, which is 2 to the power 55. Okay. AES بقى is required. AES is required to have a key size that starts from 128. So starting from 128, there is of course 256 and more. So AES, assuming again we use brute force, so it would be like 2 to the power 128 bits, which will require huge number of years to break with the key size of 128. So the key is the key size actually, but the factor that we يعني focus on when it comes to AES is actually the complexity of the algorithm itself, what we will talk about in a minute. So triple this uses a key size which is triple this. So if you multiply this by 3, the triple this has a key size of 168. Okay. So which is يعني the barely feasible given the servers or the computational capabilities that we have nowadays. So that's why NIST has actually recommended the deprecation of using this in any system, and has actually recommended to use triple this instead. So if you have this, what you need to do is to convert it to triple this by using 3 chips or by using 3 duplications of the same this to have or to represent triple this, in which case the security level would be much higher. However, as you will see in the assignment, يعني triple this is hugely complicated. It's very, very complicated, and it takes huge amount of time for encryption and decryption. And I have to warn you, for assignment 2, you have to possibly run MATLAB for sometimes 2 days or more to get the results of the encryption and decryption. So you will see how complicated triple this is. Okay. AES uses a key size of typically 128, 192, or 256 key size, which increases the security level much, much higher. However, again, the key here, or the important factor for AES, is actually the complexity of the algorithm itself, which we will see how we can make it much less complicated compared to this and triple this. So triple this is nothing but repeating this 3 times, and we apply the this at 3 stages by doing key 1, key 2, key 3. So we divide the 168. So these 3 are 168 bits. So we divide the 168 into 3 parts. Each part is 56, 56, 56, and then we apply this, and we do it in a chain fashion like this. So for, of course, the decryption, again, you will have to experience this in the assignment. We have to, of course, we have to do the reverse operation by applying key 3 and then K2 and then K1. So we have to do the reverse operation. So the decryption has to happen the other way around. You have to apply the last key first, okay, which makes okay, so triple this is recommended in FIPS 46-3. Triple this is approved as a symmetric encryption of choice by NIST, and it's actually recommended to replace any system with this implementation, because this has been, proven to be breakable, not because of the algorithm itself, but because of the key size. Okay. So government organizations with legacy DIS systems are encouraged now to transition to triple DIS. Okay, so it's anticipated by that the triple DIS and AES, they will coexist as FIPS approved algorithm for years to come. Triple DIS and AES, although AES is much less in terms of complexity, but we have very huge amount of legacy systems that uses DIS and triple DIS that we don't think they will vanish anytime soon. So the triple DIS and AES will coexist for years. So in 1997, NIST issued a call for proposals for new, encryption algorithm that it should have the same security strength like triple DES with much less complexity. Okay, and as we will see, the AES with a key size of 128, it can be stronger in terms of strength, security strength, compared to triple DES, and at the same time, it's much less complex. Okay, so the implementation complexity is much lower, which makes it software implementable. So you can implement AES using software. And as we will see again in assignment 2, is that AES spends much less time to encrypt and decrypt. Okay, so NIST selected the proposal from Regendile as the proposed AES algorithm, and they published that in FIBS 197 to recommend this AES algorithm, which is proposed by this scientist. So that's how the AES looks like. So the fundamental difference between AES and DES is that, as you will see, AES here is based on byte level. So you will see that the key is 16 bytes. Okay, so we don't anymore deal with bit level operation. We don't do like bit level operation. Okay, so even when we do here shift rows, as you will see for shift rows and everything, you will see that we actually do a shift for entire byte. So we don't do bit operation. We don't do bit level operations at all. So what we do here is byte level operations and matrix multiplication, as we will see for this mixed column stage. So the way that the AES works is that first it adds the stage which is called add round key, and the add round key is nothing but the Vernam cipher. So this is simply the Vernam cipher. Add round key is just XORing the subkey, of course, which is generated using the subkey generation algorithm. So the key here is 16 bytes, and we generate multiple subkeys out of this 16 bytes, and each one is now XORed with the plain text to perform the XOR operation using the Vernam cipher. Then we have 10 rounds as opposed to 16 rounds in physical structure or in the DES operation. Here we have 10 rounds only. Okay, again, why 16 rounds? Why 10 rounds? Okay, you might ask yourself, why 16? Why 10? So that's again based on some information theoretic analysis, which we will not get to. Okay, so each of these rounds, unlike the physical structure, it actually uses 4 different operations or 4 different stages. First, we use substitution, then we do shift rows, and we will talk about each of these steps. So the substitution basically is the fact that you take each of these words. Actually, here the key is 4 rows and 4 columns. So if you make it straight as a vector, it's actually 16 bytes. You can make these 16 bytes 4 by 4 matrix like this, and each of these bytes, it can be used as 2 hexadecimal digits. So these hexadecimal digits will be used to look up the value for the substitution, as we will see. Then the shift rows is nothing but the fact that we shift one of the bytes to the left or to the right one stage. Then we do the mix column, and the mix column is nothing but matrix operation. Matrix operation. So we'll see how this is done. And then at the end, again, we use another stage of Vernam cipher or add round key. So these are the 4 stages for the AES round: substitution, shift rows, then mix column, and then at the end, add round key. Okay. So we'll talk about each of these steps, اللي هي ال 4 stages in each round. So the substitution or the S box, we will see that again the input text is 16 bytes, which can be converted into 4x4 matrix like this. So each 4x4 matrix is 1 byte. 1 byte is in fact 2 hexadecimal digits. Each one is 4 bits. Okay, so we deal with hexadecimal digits. So we have 0 and 0. From these 2 hexadecimal digits, we have to use this lookup table. And this lookup table is given and it's fixed. Okay, it's part of the standard, it's given and it's fixed. Okay, so for example, 0 and 0. So we say 0 here and 0 here. So we convert 0, 0 to 63. Okay, and then the second byte is 3C. So we get 3 and C, which is EB, and so on. It's a very simple substitution based on fixed lookup table. So this is the S box substitution. So again, the difference between this one and the this is that, again, for this, we have to, even the S box was based on the bit level operation. So we take each 6 bits, we take the first bit and the last bit to represent the row, and the middle 4 bits to represent the column. Okay, and that was actually very complicated unnecessarily, because again it forces the implementation to use bit level operations to get each and deal with each bit separately. By dealing with byte level operations, we can make the implementation much faster. And not only that, as we will see when we talk about matrix operation, we know how to do that very efficiently, and that makes the implementation much more less complex. Okay, so the first stage is the S box substitution, and that's very straightforward based on a 4x4 matrix. We call this, by the way, we call this the state matrix. So in assignment 2, you will see in the code the variable name state matrix to represent the input to the S that we perform here. The shift rows is very simple. It's also very, very simple. So, and that's the key actually for AES, is that it's very simple to describe. So the first, again, we convert the state matrix into 4 rows. As we know, the state matrix is a matrix of 4 rows by 4 columns, okay, to represent 16 bits. Very easy. So the first row will be as is. We don't do anything. The second row, we shift 1 byte to the left. Okay. The third row, we shift 2 bytes to the left. Very simple. And the third row, or fourth row, sorry, we shift 3 bytes to the left, which is actually 1 byte to the right, yani, because we are talking about the circular shift. Okay. So the shift rows is very, very simple stage. So the first row stays as is. The second row, we shift 1 left. The third row, we shift 2 left. Fourth row, we shift 3 left. That's it. So it's very easy to describe. And that's, again, one of the strengths of that algorithm, is that all these stages are easy to describe. So if I were to explain it to anyone, it's easy, and that's a good feature, because then the information theoreticians can take that and and work on it in terms of strength boundaries and so on. ماشي كده؟ This is just an this is the shift rows. We perform the shift rows as part of the round for AS. يعني so we can perform this shift rows in any way, but that has nothing to do with randomness or unpredictability or something like this. This has to do with the fact that when we perform the operation this way, we make it very difficult for the attacker to kind of guess the original key itself. By doing these operations repeatedly, the attacker has nothing to do but to do brute force. But the random generating question so far, the metric, the mixed column is very simple. We have a predefined matrix, and again, do not ask me why the matrix looks like this. Huh? Again, this is based on some information theoretic analysis, and then we multiply this by the state matrix. So we simply multiply the state matrix by a predefined matrix to convert the state matrix into another state matrix for the output of this mixed column stage. Of course, the add round key stage is very simple. We convert the state matrix into one big vector of 16 bytes. Okay, and then we XOR it with the key. That's it. واضح? Okay, so the add round key itself is a very simple stage. So again, the 4 stages are very simple to describe. First is the substitution. In the substitution, we take each byte in this state matrix, and then we divide it into two hexadecimal digits, and we use a lookup table, a predefined lookup table to substitute the value to another value. And in the second stage, we do shift rows, where we take the first row as is, the second row we shift it to the left once, the third row we shift it to the left twice, and the fourth row we shift it to the left three locations, and so on. And then the mixed column is actually a matrix transformation, which we know how to do very efficiently. So by doing these 3 stages or 4 stages at each round, and we do 10 rounds of these, it is proven from based on information theory that it has the same strength like the triple DES, okay, with much less complexity in terms of implementation. Shift rows are different, and it's proven to actually be implemented very efficiently even in software. Okay. So any questions so far? Okay. So the process of random and pseudo-random numbers, it's actually an ingredient process in many operations. So we use the random number generators to generate, for example, the keys. We use it to generate public keys in some cases, although for RSA algorithms, as we all know, there is the Q and there is the P prime numbers. So we have to generate these prime numbers based on certain logic, but in any case, we can use some random sequence of bits to use it as a key in some cases. And in many cases, some key distribution servers, they use these pseudo-random generators to generate random keys every now and then and distribute it to the different communication parties on a regular basis. So there are 2 distinct characteristics that have to be fulfilled in any random number generators. The first is it has to be truly random. And we will see how we measure the level of randomness for any sequence of bits. How do we measure the randomness, the true randomness of this key sequence or bit sequence? Okay. The second characteristic is unpredictability. Unpredictability here means that if I know part of that bit sequence, is there any correlation between that part and any following parts? Okay, so if I have sequence of bits like this, let's say 128 bits, and this is like the key for AS مثلا. Okay, so true randomness here talks about the fact that you cannot have anything that reduces the amount of guesses that you have to do in order to get this bit sequence. So in other words, if I tell you that this pseudo-random generator produces more ones than the zeros, let's say مثلا 75 ones and 25 zeros, 25% zeros. Okay, so in that case, what I could do is to play or to guess on the less number of states. So if I know that 75% of the time the random generator will generate ones, so in that case I will guess the zeros, because if I guess the zeros, it will be I will have less combinations, right? So if I know that, go ahead. Mhm. You mean that like for the shift rows operation? لا هو random generators, as we will see, these are just some software or hardware that generates random bits. Okay, generate random bits like 1001 and so on. So if I have sequence of bits like this, okay, how do I know that this is truly random? Okay, so NIST recommends one of the tests that they do on key distribution servers is that they recommend to have the for any random sequence the number of zeros equals to the number of ones, more or less, which means that the random generator should in fact generate sort of equal ones and zeros. Okay, why is this? Because if the random generator generates more ones than zeros, then the attacker will play on the zeros, which means that the attacker will say, okay, so I know that I have مثلا 20% of the bits are zeros. This reduces the number of combinations right there, right? If I know that the number of ones are less, alas, I will work on the number of ones. But if I know that they are equal, I don't have anything to really guess in that case. So I have to work on all types of combinations, which increases or confuses the attacker even more. Okay. So if I know any piece of information that the number of zeros less than the number of ones, I will work on the less number of combinations, which will reduce the guesses of attack. So this is what we call true randomness. Unpredictability is different. Unpredictability says, okay, so if I know part of that bit sequence, okay, if I know the part of that bit sequence, will I be able to predict the other part of that bit sequence or not? Which means, is there any correlation between part 0 and part 1? Are they statistically correlated? Okay, so that's what we mean by unpredictability. So these two features need to be fulfilled in any random key generator. It's very, very key. Okay, very, very important. Okay, again, random number generators, as we will see later, they of course we don't have in software we don't have purely random generators. We always have pseudo random, and we'll talk about the difference between true random and pseudo random. Okay, ماشي? But in both cases, these two features need to be fulfilled: the true randomness and the unpredictability. So, so the randomness means that you have uniform distribution of being in any stage. Okay, so if you have equally number of zeros and number of ones, then you can achieve this uniform distribution, because taking any state of the bit sequence, as we said before, if we have a key of length k, okay, and this is uniform, it has uniform distribution, which means that the key can take any combination with the same probability. So any combination here has the same probability, okay? But if you have more zeros than ones, or more ones than zeros, then it becomes something like this, or something like this. So the distribution will become not really uniform. So you have more probability to take certain combinations more than the other. So the uniform distribution is very, very key. So the uniform distribution is very, very key for these types of random key generators. And also independence. So no subsequence can be inferred from the other subsequence. So there is no correlation between these subsequences. ماشي كده؟ So in applications such as reciprocal authentication, by reciprocal authentication here we mean that the sender authenticates himself or herself to the receiver, and the receiver does the same to the sender. So both of them, they authenticate each other. Okay? So in that case, there is a session key generation that gets generated as part of this process. So as part of this process, this key generated needs to have these two features. It needs to be truly random and needs to have unpredictability. Okay, so care must be taken that an opponent not be able to predict future elements from knowing one element. That's what we mean by unpredictable. So this is the difference, and this is the last slide we talk about. So this is the difference between truly random generator and pseudo-random, and what we call pseudo-random value, or context-specific pseudo-random generators. So the true random generators, they take any true random source, and one example of this is what? Can anyone guess? One example of يعني true random process. Okay, one example of true random process. People who are talking about, who are working on physical layer security, they know that the channel models, the wireless channel models, they are true random process that you can use to generate a random sequence without any seed, without anything. So that's why people who are working on physical layer security, what they do is that they try to take some measurements from the channel between a source and destination, and use that channel state as a random process to generate a random sequence. Once you generate that random sequence, you can use that random bit stream as a key as part of AES or something like that. Okay, so in that case, what we do is that we take a random source and then we do A to D. That's all what we need to do. We convert it to binary. Yani we do A to D. We take a random process, like for example, channel measurement, wireless channel measurements, and then we do A to D, analog to digital. Yani. Analog to digital, we convert it to random bits, and then we take these random bits and then we perform the nest test in terms of randomness, unpredictability, and so on and so forth. The second type of random key generators or random bit sequence generator is what we call pseudo-random. For pseudo-random, we take a deterministic algorithm. This deterministic algorithm could be a cryptographic algorithm or encryption algorithm. So in that case, instead of using the key, we use what we call a seed. So the pseudo-random generators, they take a seed which constitute like a state, and then they use any kind of deterministic algorithm to generate an output. This output is not truly random. It's not يعني completely random. So we call it pseudo-random. Okay. So another third type, which is what we call the context-specific value random generators. In that particular category, in addition to the seed, we use context-specific values. Context-specific values could be like the certificate. For the case of certificates, could be like user ID and password, okay, which is exclusive to a person. We take the user ID and password with the seed, and again, we use some kind of deterministic algorithm to generate a certificate of some sort. So this pseudo-random value will have embedded in it, will have the context information or the user ID and password. And we'll see how to do this when we talk about certificate generation. Okay? All right, so that's so these are the three categories of random generators. And again, we use these random generators very, very commonly, and we'll talk about them when we talk about RC4 next time, inshallah. So we see how we can generate the random sequence to perform the RC stream cipher. Any question, Shabab, so far before we switch to the seminar?